Walls, as this thing has separated many, many different times. Okay, and so this is my excuse to show you about the bola spider, but it also shows you something about that you've seen this kind of thing before. Every time you go out in springtime in Chicago, at least springtime in Chicago, you have spider webs out there, and after a nice cool night and you have dew everywhere, you see that the spider web in the morning is decorated with these beautiful little drops of liquid. That's just the same thing happening, but in a more conventional thing that you know about. Okay, so this is how this instability starts, and then it ends at some point, and so what we're interested in is how does this instability end? And so what I have here is two pictures of just the end point, as close as we could get to where the drop was breaking apart. And these two things look nearly identical. It's hard to tell apart. And I'm showing you two of them to show you how close they look to one another. But I didn't show you the rest of the drop. And so now I want to show you what I hid from this so you can see what it was that was where these came from. And so these are the two drops that they came from. And so I just uncovered what I had in before. And so you can see this is this region here, and this was that region there. So it's the same thing. It looks the same, but they look very different because what I did with this photograph was I turned it upside down. And so if I turned it upside up so that it was the right way of looking at the way it really would have appeared in the movie, what you see is that I get the same behavior down here, point with the cone pointing into the sphere, which is the cone is pointing in the direction of gravity. In this case, I get the cone pointing up into a sphere, and this time it's pointing in the opposite direction of gravity. So there's something here that didn't depend on the forcing that actually got this thing to go in the first place. It was gravity that pulled this thing down, and somehow this thing managed to do the same thing. And so there's something about these drop breaking apart which is universal. That is, it didn't matter about the details of what I was doing. That is, there was something universal about how the drop broke apart. And so that's what I want to emphasize here. And so what I want to show you now is a movie of this drop breaking apart. And I should just tell you just a little bit about how this movie was made. I mean, this was made in our lab in Chicago, which is a very old and decrepit lab, and it's so old and decrepit that the drop is actually going to go sideways. Okay, so gravity was pointing sideways. And so, of course, what we did was we turned the camera on its side so that we had the long aspect ratio. But that's what you're going to see the drop start here and move across the screen, and that is really the direction of gravity. The other thing is that this was taken around 10,000 frames a second and played back at 30 frames a second, so it's a few hundred times slower than what would really happen in real life. And so this is what happens. And so from here to here is about 1.5 centimeters. It's being pulled down. You will see the cone pointing to a sphere in a little bit, right around there. Okay, so I want to show you this because, I've been at pains to try and tell you why these are important scientific problems. But if you ask why am I really doing it, it's because I also think they're beautiful problems. And that this, if you are really honest with you, this is why I come to the lab every day, not because of Zeno's paradox. So this is the thing, and I'm not supposed to say that, so don't tell my NSF people, but that's really what drives me in this, and I'm not ashamed of it. So that's why I'm telling you here. Okay, so that's how the water drop breaks apart. But every unhappy drop is unhappy in its own way. And so these are different drops. So this is what you've seen already, which is water falling in air, and you saw the cone pointing into the sphere. This is basically just a more viscous form of water that we took what's called glycerol and mix it with some water. So glycerol you're familiar with because you can buy it at the grocery store or the drugstore, and you can either use it for making cosmetic things, but also to make stronger soap bubbles for your kids if you want to make big soap bubbles. And you probably have a little bit more intimate knowledge of this because I've been told that McDonald's puts it in their shakes to give it that je ne sais quoi de McDonald's. I mean, they call it body, we call it viscosity, but it's the same thing. So this is a more viscous form of water falling in air, and you see the shape is very different. That is, it's a long, long cylinder, and then it goes unstable and forms a thin thread. And if we had taken another picture just slightly later, you would have seen this thread go unstable and form an even finer thread. So there's a recurrent thing going on there. This is the pure glycerol on the inside here falling inside another liquid. And so it's an oil, and so they're immiscible with each other. It will still fall if one is heavier than the other, and it will still break apart. And this is another kind of instability. This is a cone pointing to a cone. And this one, I don't know if you can see in the back row, but in the front row, maybe you can see that this is still connected by the thinnest of threads here. And why nature decides that's the way to break up, drop apart is, I mean, I find fascinating that it goes to this length to do such a thing. And so we get, as an experimentalist, to choose which regime we're in because we can vary certain parameters. So what parameters do we get to vary? We get to vary the viscosity of the inner fluid, viscosity of the outer fluid, the density of the inner and the outer fluids, and the surface tension that I keep telling you about, and then this nozzle diameter. And after I've done that, these are basically all the parameters for simple fluids that I get to change as an experimentalist, and I get to tune which regime I want to study in here. And so what I want to now go on is talk about, well, how should we think about this drop breaking apart? And so this is one idea which is, I hope I can get this one idea across. And so it's a little bit, it's not a trivial idea at all. So it's this idea of using scale and variance to try and understand something about that singularity. So what I kept telling you before was that the breakup, when the drop breaks up, the radius is smaller than any other length in the problem. And I kept emphasizing that over and over again. It's not smaller than the molecules, I don't mean that, but smaller than any of the other length scales, such as the drop radius, the length scale on which gravity matters, the length scale on which viscosity matters. These are the various things, scales that you could define. And because this drop neck is going to zero, it's going to eventually get smaller than any one of those other scales. So it's infinitely smaller than any of those other scales at some point. And the idea is that the dynamics can only depend on the thickness of that thread at that point, that smallest point, and not on any of the other length scales. And so, I say that in, not okay, he knows, but why do we say something like that? And so what I want to give you some feeling for this is that if you think about rain coming down on a mountainside, and so the rain comes down everywhere, and it flows into these mighty rivers, and these rivers cross the continent, and then they get to the Gulf, and in the Gulf, this river breaks up into smaller rivers, brooks, rivulets, and finally the water flows between two little pebbles in the stream. And what I want to ask you now is, does the flow between those two little pebbles in the stream depend on the fact that the water originally came from a mountainside? No, it doesn't make sense, right? It's forgotten all of that information. It can't keep that information because that was so long ago, that stuff has been erased because it's on a different scale than the scale at which the real thing matters. And so that's the same idea here. That is, the neck is the smallest thing in here, and the flow in that neck doesn't care about those other length scales because they're irrelevant at this point. And so the flow only depends on that shrinking radius, but that shrinking radius depends on the flow, which depends on the radius, which depends on the flow, which depends on the radius, which depends on the flow, radius, flow, radius, flow, radius, flow. And so what I've done here is I've created a fractal sentence. That is, I blow up any part of the sentence and I get the original sentence back. And so this should remind you of one of those things I showed you earlier, the trees, for example, where I blow up on one scale and I get the entire tree back, at least statistically. And so that's the idea here, that this is what gives rise to this self-similar structure. You blow up any part in this system and you regain the original form back that they were talking about. And this is what gives rise to these universal shapes. And so our job as experimentalists was to try and go and see if this worked. And so what I want to show you here is what the mathematics of that picture that I just showed you was. And it's this particular form. What it's saying is that there are two length scales at this point. One is this scale and the other is this scale. And what I get to do is, if I know what the shape is at one point, if I want it at a later time, I just multiply this scale by something to get it smaller, and I multiply this scale by perhaps something else. And I just do that over and over and over again, and I can get as small as I want. And so this is a data, and I don't want to go into what this data is, but the reason I'm doing this in a public lecture is because you should realize that what we do is not just taking pretty pictures, but that, this is painstaking data to get each one of these points to really be able to understand what that's doing. And so there is real data behind all of the pictures that I'm telling you, and this is just a placeholder for all of the data that I'm not showing you tonight. And so again, this emphasizes what is universal. And now you ask, well, is this picture truly the case? And then I ask about, well, what happens if I did the opposite of what I just did? So before, remember, we were talking about water falling in air. Suppose I did the opposite of that, which is air rising in water, otherwise known as an air bubble rising. And so this is work that was done by Nathan Keim, who is back there, and so he did this when he was with us. And so what I want to show you is a very careful experiment that he did. This was a very circular nozzle, very carefully leveled, so this is as level as he could make it. And now we will see how this thing starts to rise. And so it's rising. You get the same kind of thing. And you can see a little drop went up at the top and comes down. It's, again, a beautiful set of a beautiful movie here. But what was bizarre about what I just said was that I went to great pains to tell you that Nathan did a very careful experiment, and very circular and very balanced. I didn't tell you that about any of the other experiments. I mean, I just said this is the way it was. So why did I tell you that about this case? And the reason I told you that about this case is that there's something fundamentally different here than in that other case. And I can show this to you in the most blatant movie that I've seen, which is just focusing on that region in the middle. And we will see this happening. And now we've done something to make this as non-circular as possible. It's a slot nozzle, and we blow the Nathan had the air come out rather quickly at this point, and now we will see what this looks like, and you'll see that shape. It doesn't look like that simple thing that I've been showing you all along. Something very different is here. There's structure on all these different scales, so let's go back and see this once more. Let's see if I can. Okay, so if I go here, for example. I mean, so this is this neck breaking apart. This is not the smooth variation that I've shown you in all the other ones. This looks like the liquid was torn, and like a sheet of paper tearing from this thing from one side and the other side. You get these different pieces coming in, and I remind you that there's nothing less likely to tear than air and water. And that's all that's going on here. And so something very different is happening in how this drop, or this air bubble, now breaks apart from the other cases that I told you. And so, again, to wrap up this part of the story, it's a different kind of singularity, and it, again, has some relation to human life, in that we always have this debate about raising kids, whether it's nature or nurture. And that same story is here. So, in the case of the water drop falling in air, it forgot about everything about its initial conditions. The shape of this singularity was universal. That is, it only depended on nature. It didn't care about how it was raised or how it was treated in the process. So there was no memory, again the word memory for the memory program we've been in, there was no memory of what the initial conditions were, but in the case of the air bubble rising, it remembers nearly everything about how this thing started off. And so this is a very different type of beast. And again, it has this relationship to things that we kind of feel about. Is it nature? Is it nurture? And that debate rages even here. So this drop has fallen, and now what does it do? Well, it has to hit something. And so this is an example of something that you may have seen in your in various fountains, where you have water coming down in a nice stream, hits a flat surface, and then creates this water bell. And you can do this in your home. That is, you just take out the aerator from your faucet and let the water fall down on the top of, let's say, the soda bottle, and you'll see a beautiful bell coming out, just like this one here. So this is a similar thing that you've seen. And the question we want to know is, how general is this behavior? And so what I ask is, well, suppose this is water doing this, but suppose I had grains of sand doing this. And so what I have showing here are grains of sand hitting this the surface, and it doesn't look like that at all. That is, each grain of sand comes in and does exactly what you would think. You throw a ball at a wall and it comes right back at you. And so this is what you would expect from individual grains of sand hitting this platform. And now the question is, well, how about if I had taken a jet of granular material? So it was a little bit more like that water case where I have a whole jet of the water coming in. And so that's what this experiment is. So what we have here is, we have the target up here. We have a tube pointed at the target. We have sand up to some point here, and we have pressure back here. We suddenly let the pressure go, and we just spit out this whole jet of white sand. And so the white sand starts here. And when I start the movie, you'll see this white sand starting to move down this tube. Okay, and then what do you think is going to happen? Is it going to ricochet in all directions, or is it going to behave like a drop of water? And so here is the movie, and so watch this white sand coming down. It's a target. And so it's behaving like liquid. That is, it's not curling up on itself because there's no surface tension here, but it is going out in all directions in this very, very thin sheet, just like that water belt was doing, that very thin sheet in all directions. And so that's what's happening in this case. And so what changes between that single particle and these many particles, that's with the individual particles hitting the wall and coming back at you, versus the liquid, or that the jet, was that it was the thing that we needed to know was how many particles are in the diameter of that tube. So that's how many particles are in that cross-section. So if we have very small particles, 100 microns, so this is a tenth of a millimeter, we get this very nice thin sheet. If we make it 5 times larger, you begin to get fireworks. When it's 20 times larger, you get this thing really sparkling all over the place. So the granular material is really behaving much more like these individual particles coming back and forth and hitting yourself. Okay, so again, what does this have to do with anything else that I want to tell you about here is that there's, again, a relationship here to a variety of other areas of physics. And so I was able to make a liquid, and I was able to do this without any attraction. The grounding material wasn't attracting itself anymore, any more than it was before. And we know grounding material is not like a fluid, and it's not due to confinement, as if I was holding this thing in a box and holding all this stuff together, and so that it might look like a liquid for that case. But it's just the kinematics of the situation which is driving this thing to look like it was a liquid. And why is that interesting? Well, it's a classical analog to a very famous experiment that was done a few years ago and still going on at the RHIC collider at Brookhaven and at CERN, at LHC. And this was heavy ion collider physics, and what they did was they took two heavy nuclei, two gold nuclei, and bashed them at each other as hard as they could, and what you get is a quark-gluon plasma. So this is the stuff at the very beginning of our universe. So this is where we all came from. And the big surprise that they reported was that the quark-gluon plasma was a liquid. And the reason that it was a liquid that they could tell was that as this liquid expanded, if there was a thin slot, it expanded in the directions perpendicular to that slot. That was the fastest direction. And so here we have a slot going in this direction, and this is looking at that same experiment from the back. And you see the same kind of behavior. So this is extending in the thin direction rather than in a uniform direction. And so this is the same reason that the quark-gluon plasma is the same reason for its being a liquid as this granular gas is liquid. And the only thing I would say is these experiments cost a few $1 billion, and I think ours came at $50. And so there's a slight difference, but we're not bragging. Okay, so this is one question about how this liquid is formed, and it raises interesting questions about what it means to be a liquid. So very fundamental questions that you get to at these simple tabletop experiments is to basic questions such as this. So how many collisions do you need to have for it to be a liquid, for example? Okay, so one other thing that drop could have done is if it had fallen on a plate, and then what you would get is a splash, right? So if that drop that had detached comes down and hits a plate hard enough, it's going to splash in all directions. Okay, so what we were interested in is, well, is there anything interesting in the physics of a splash? And so what I want to show you now is a movie of a drop splashing. So this is a drop of alcohol. It's about 3.5 millimeters in diameter, so pretty small drop. It's dropping from something like this height, so nothing fancy about this. It's going to hit this at a few meters per second. Everything very normal, just ordinary stuff. And the one thing I should point out is that this white thing in here is nothing inside the drop. It's just that this drop is lit from the back, and so you see it's basically imaging the light source, and that's all that white spot is. So let's see how this drop breaks apart. Splashes. So I think that's rather beautiful, and I don't know about you, but I'd like to see it again. So, oops. So let's see it again. So it's coming down. As soon as it hits, it grows that corona, and that corona then breaks apart and splashes in all these different directions. And so the question is, well, what causes a splash? And so we've talked about the liquid, and so it can be, how big is that liquid? If it's a big drop, we know that's going to splash more easily. If it's moving very fast, it's going to splash more easily. So if I take a tiny little drop and lay it very carefully on the table, it will probably not splash. So we know the size and speed matter. These other things I told you about, like the surface tension, holding this thing in, that's going to matter, because how this thing is spreading apart is going to, what's holding it from spreading apart. What its viscosity is going to matter, how easy this fluid flows. And then, of course, I need to know about what is the surface. Is it a hard surface, soft surface, wet surface, dry surface, smooth or rough? These are the only things that matter. And after that, I've told you everything that you need to know. Notice I didn't say anything about the air around us because, that doesn't matter. I mean, I don't even feel the air, really. And the last time you felt the air were worried about the air in the room was when you were running up a flight of stairs and were gasping for oxygen, not because you felt the air in your face. Okay? But you do know that if you stick your hand outside the window of a moving car, you feel drag on your hand. And so it gets pulled back. So what we would think is that all these little drops that are moving out there are feeling drag because of the air there. So if we took the air away, we could get a really big splash. So this is the idea. So we want to show a truly high-class splash. And so I'm going to show you this movie again. And so this is the third time you've seen it. So get it into your mind. So this is an ordinary splash. Hits, forms some corona, and the corona breaks apart, and that's where the splash comes from. And now I'm going to do exactly the same experiment. So it's the same drop of alcohol from the same height, same size, same microscope slides. The only thing is that we put in a container that we could take some of the air out. So this is 1/3 atmospheric pressure. So this is the pressure that you would have gotten if you were at the top of Mount Everest. So you could live in here. You wouldn't be happy, but you could live there. Okay, and so now let's see the very big splash that takes place. So here it comes, big splash. So in the words of I. Rabi, who ordered that, right? I mean, this is the thing, is that this was not supposed to happen. And so after this, we were on the floor laughing hysterically for about a month. And before we said, well, I guess we better start doing some experiments to try and understand something about this. But, those experiments are still going on today, so this is not particularly easy nut to crack. But what I want to just show a few other movies of this. So this is now the same experiment, but now all we've done is we have a higher viscosity fluid instead of the water. So it's 10 times the viscosity of the alcohol. So it's the same thing, the same drop size, basically falling from the same height. And so we want to see whether this would splash. And so this is at atmospheric pressure, 101 kilopascal. So that's just what we're feeling now. So I let this thing go, it falls. And I stop it here because it's clearly not going to splash, right? It's just spreading out smoothly, right? Okay, so let's just finish this movie. And okay, I lied to you again. But I'm telling you these things because these are... You've seen this before, but this is what we expected when we first saw it. This is not, so I'm trying to put you in our frame of mind when we first saw this. So this thing does splash, but it splashes with a very different... So we do this thing in reduced pressure, and yep, air still matters. That is, if I take the air away, it stops splashing. So this is a very robust effect. So that what this is saying is you will not get splashing on the moon. You might get it on Mars, but not on the moon, because there's no atmosphere in that. Pardon? Everyone asks that, but you know what high pressure is? Another word for that is called a bomb. And so we try to avoid bombs in our lab, and we would do that if there was a reason to do it, but we haven't done that. Okay, so I'm ending up. I just want to show this one last thing. So there's lots of studies you can do with this. And so one of the questions that comes into this is, where does the air matter? And so we look underneath the drop. Is the air mattering there? Is it mattering someplace else? What I want to show you is looking at what's happening above the drop. So is the air mattering as the drop is spreading above this drop? And so what I'm showing you now is a type of photography called Schlieren photography. And this is helping you see the contrast between different index of refraction of the air in different places. And so I'm going to show you just a little bit of this first. So I stop it here so you can see what I want you to look at. The drop is this big black thing. That's kind of uninteresting. That's not what I want you to see in these pictures. This black thing is a substrate. That's not what I want you to look at. What I want you to look at is, you can see something about the wake of this behind, and that's what this kind of photography is helping you pull out from the that you couldn't easily see with your eyes. Okay, and so now let's see this whole movie go. Now I'm not going to stop it, and you'll see the whole thing. So if there's anything that maybe you can take away from this lecture is that when you go home tonight you have a leaking faucet in your bathroom that's keeping you up at night. You can at least think that every time you hear that drop pop, something really beautiful is happening, and that shouldn't bother you so much. Okay, so this is one takeaway message. And so this is where I want to conclude, so I just want to end up with all of this. And so, I've been talking about the emergence of structure and various things, all having to do with fluids of one kind or another. And it's nature's textures, what really gives the texture of our world. And so I think that's something that I'm fascinated with, what gives it the flavor, the texture of what we deal with every day. And so I think it helps give appreciation to the world around us. I hope that each one of these things has been a surprise to you, because it was certainly a surprise to us when we came across this. The other thing I want to emphasize is that there have been connections throughout for all the science. So the things that we could do on this tabletop had things having to do with biology, had to do with memory, it has to do with the quark gluon plasma. All of these things are in different realms of physics, but we could learn something deep about them by these experiments that we do right here. And so what this is kind of showing you, these are some of the images, but nature reuses the same ideas in the different phenomena. That's the point of this. These things that appear on big scale, small scale, wherever, nature is using those same ideas over and over again. And we as scientists reuse the same ideas to explain them. And so this puts me in mind of this beautiful quotation from another philosopher, Albert Whitehead, which says, "A great idea is like a phantom ocean beating upon the shores of human life in successive waves of spectralization." And I think that really captures something about what we're all after and about how we see the world. And with that, I just want to say actually who did all the work in our lab. And so this is various people in our lab. So early work that I showed you with the powder formation and these kinds of things in the toes and fingers was done by Irmgard Bischofberger and Radha Ramachandran. You might have seen Irmgard earlier a couple of weeks ago. All of the stuff on the drop breakup was done by these people, Michael Brenner, Isaac Cohn, my colleague Wendy Zhang, and then Nathan, who we introduced back there, and Laura Schmidt, who was Wendy's student. The the water dome, water bell work was done by Jiang Sheng and my other colleague Heinrich Jaeger. And then all the work on the splashing was done by all of these people. And so these are Irmgard, but postdocs, graduate students, and undergraduates who've worked in my lab. And with that, I want to thank you very much for your attention.
Okay, question? Let me hand the mic. There's a mic in the back as well. I have two questions. The first one is, what would these effects, how would they change in zero gravity? And the other question is one that I think Feynman talked about and tried to figure out, and I'm not sure I ever did it, as why does a spaghetti strand not break in two pieces when it's been I don't know if you know the answer to either of those.
Okay, so let me try the one with zero gravity, because I am not going to try Feynman's question. So, just so we're clear about this, so in zero gravity, so you have to ask, well, would the drop fall at all? And so presumably you don't want you want the drop to be impelled in any case, so it's actually going at some velocity. So we're using gravity to push it. Yes, I mean, so I think all of those things, so gravity, as you saw when I turned the drop around, drops out of the picture for many things because it only works on objects that are bigger than a certain scale. And the objects that we were interested in this talk were all kind of smaller than that scale. And so gravity was really not an important ingredient in the analysis of what we were doing at the end, but although it was an important tool to get the drop moving, to, you wouldn't get the splat without the gravity having pulled it down, but you could have done it by other means. So gravity was not a crucial aspect of this.
Have you tried this with non-Newtonian fluids?
So we have...
What is a non-Newtonian fluid?
Non-Newtonian fluid is... so there are a variety of different kinds of non-Newtonian fluids. Everyone know what oobleck is? So oobleck is cornstarch that's been mixed with roughly 50% water, dirt, water, 50% water, something like this. And it's beautiful. You can walk on it because it withstands rapid motion, but if you can stick your finger and stick it in slowly, and so it has also beautiful properties. Other fluids are polymeric fluids, and so to take a silly putty, remember silly, and you watch that move, and that is fluid, is it not? It's a mixture of the various things because of the molecules that's part of this. And so there are all sorts of things. One non-Newtonian fluid, which I did mention, was the granular stuff. Sand is a non-Newtonian fluid. To the extent that it's a fluid, it's really not behaving exactly like a Newtonian fluid. And so there are other aspects that come in because of the large size of the particles. So all of these, and everything in your kitchen is a non-Newtonian fluid, basically. Anything the chemical companies have got their hands on is non-Newtonian. I can probably guarantee that. And so there are things, so we haven't done those non-Newtonian fluids, but other groups have. So they've looked at things having to do with the drop breaking apart. And there are differences depending on what the constitutive laws are for that particular fluid. There are different kinds of things. And so our emphasis here was to take the simplest thing and see if we could understand it. That was where we went. But then other people have gone and done more on that in these different ways.
Still does the necking?
So some things still do a necking. So if you put particles in, this thing comes out and necks. So a granular, so a very dense suspension of grains in the liquid, then you can, where the grains then start poking out as this thing is falling, then you get kind of a fracture in some of those areas where the thing goes apart. So, but you do get, until you get down to that particle size, you do get this kind of necking behavior. And there are various laws that people have been able to measure for that. I mean, there were different laws than what we got in this case, but they are, but you can analyze it. Now that you know something about how to analyze it, this gives you a way of doing it. Right. Questions? So we'll do something like that.
In the Schlieren photography that you were showing, I was having trouble parsing visually the last part with the curling going on. Was I seeing half of it, and it's really like that all the way around?
Yes. So I am really surprised at how nice that turns out. I mean, it's doing this in, it's a donut, right? And so you're seeing all of it. But when you're seeing it here, you don't really see anything of the structure. And so it's only at the edges that you see the structure. It wasn't that we try to focus on just those edges. We were still focusing on the whole thing, but that's the part that comes through. So that is, you're surprised, and I'm surprised too. How nice that comes out. But these people were very good.
How much of this is really surprising to hear, for example, to Michael Brenner making something that is aerodynamic equations?
Yes, right. So when we worked with Michael on this, he was a student in and so the computer simulations that were able to be done in those days were not very good at having two different viscosities. So that was one thing. So that's something that's still a problem even now to really be able to get big viscosity contrast in these phenomena. So that's one thing. The second thing is that in the I showed one of these things. So let's see if I can go back to this one. Okay. This one, I told you, it formed long-term forms in neck. Okay, that you could have gotten from the Navier-Stokes equation. Right? But I said that the next step, if I go a little later, gets thinner. That's not the Navier-Stokes equation. That's noise. That inherently always is there because it's so sensitive on the atomic scale that even at when you're 1 micron neck size, you can still see it. If one atom was out of place, that would have been enough noise to trigger the next thing over and over again. Well, it was a deep mystery at the time. That is, we did not, before this, we did not know how to think about the singularities. We did not know that the right way to think about this is, so we learned something from this. And the other thing is that what we were told at the beginning was that all of these things should be universal. And then I showed you the air bubble, and the air bubble was not universal. And so then you ask, okay, so what's happening there? And now I can tell you kind of why that shouldn't have been universal. And everything in retrospect is obvious, Jim, but before, I mean, you know, theorists are great at predicting things after the fact. And so, you know, that was...
you get it right beforehand, you never should. It's okay.
Well, that isn't quite true. You're my best friend forever, and, you know, we'll talk about this later.
Okay, I think on that note, we'll stop. Thank you, Sid.
Okay.
Let me just remind everybody we have cookies and drinks, etc. in the adjacent courtyard, so please don't leave it on for the postdocs.
It's a really great honor for me to be able to tell you about one of my passions this evening, and I hope you will enjoy it. But any audience of mine that includes students, and I have plenty, do have to work. So you will have to work this evening as well. And let me start my lecture by making you work, okay? So I'm going to immediately disappear for a moment, and I'm going to ask you, I'm going to do a quiz, okay? Just to test your knowledge. And so we'll see how it goes. Huh?
Gracias.